Hey class, I wanted to continue on with our study of the zeta function. I imagine this will take the rest of the class, but if we finish up early, then it'll be I guess, a pleasant surprise. Okay, so to review, last time we talked about um, geometric series, right? Everything began with the geometric series, and then the Euler product was this infinite product of these forms for geometric series. So again, we'll derive the geometric series, or a general geometric series. So it starts with a sum which follows a simple pattern. So you start with 1. You can start with any number really, but we'll start with 1. And then you multiply it by some ratio. Then you multiply the previous term by that ratio. Do it again. You can do it n minus 1 times, so that the sum of n terms, right, 0 through n minus 1, is represented by this simple shorthand notation. It's a placeholder, just like the variable x. We don't know what it is, but we know that it's something, right? And so we're going to solve for it. And the way that we solve for it is by generating a new sequence. So we multiply this times r. So r times that sequence, or times that sum, right? So this is the sum, this is r, just algebraic substitution thus far. And so now again we have n terms, because this had n terms, but everything has been promoted by 1 power of r, basically, because of this multiplication. And so now this is it's more than mathematical sleight of hand. It's but it is still, it has the feel of a trick, right? We're going to solve for this by just combining these two equations, right? So if we do it like this, right, where we subtract this sequence from this sum, or sorry, this sum from this one, right, using this notation, then everything from this first one cancels out, except for the 1, the leading 1. Right, so this minus r is 0, r squared minus r squared is 0, and so on and so forth. And so the n's, the first term and the last term, the first term of this one and the last term of this one, are the only ones that are left when we perform the cancellation. Right? So we end up with this. And then we just use the distributive property to factor out s of n. So it's actually something that we can solve for now. So we factor out the s of n, and then we rewrite the equation, moving this, or dividing both sides by 1 over r, right? So it cancels out over here, ends up in the denominator over here. And so now, if we want the infinite series, the sum of this geometric series, well, if r is greater than 1, then this is going to blow up to infinity, right? Wherever, whether r is positive or negative, if its absolute value is greater than 1, then as n goes to infinity, it's it's just going to explode, right? And so that doesn't converge in general. But the whenever it's less than 1, then as n goes to infinity, those the exponentiation drives it down to 0, so that the limit of r to the n so the limit as n goes to infinity, whenever, like, if r is written as some number, right, some ratio p over q raised to some power, if p is less than q, then q is going to dwarf it, and that term will go to 0, and this disappears at the limit, right? So that as n goes to infinity, this becomes 1 over 1 minus r. And then, okay, so this is a reminder of the geometric series, that this and this, where there are infinitely many terms, right, these are interchangeable. And when there are finitely many terms, it's this, right? Okay. Alright, so now we have all of these sequences again. Right, and there's infinitely many of them. And so, again, r is written as some ratio, p over q. But even if but p and q can be any numbers that we want, right? So the one that we're gonna substitution we're gonna make is to make it p to the s over q to the s, and then each one of these ratios now becomes p to the s over q to the s. And so whenever we do that, that power just carries right through. Okay, so for the series that we were interested in, everything was of the form and 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s. So p was 1 in all of those situations, and then q was just whatever the next natural number was. Okay, and so we represented this using a product of these geometric series. In fact, using all of it was over all of the prime numbers, and so the factors were everything that could generate distinct terms. And what I mean by that is if we had used the ratio 1/2 and then we again used the ratio 1/4, well, 1/4 4 is not prime, right? So everything that was a multiple of 4 would be repeated between those two. So we want distinct contributions to our Euler product, right? And so we use prime numbers to get that guarantee of distinctness. And then whenever the infinite multiplication takes place, then you get all of the composite and the prime numbers from that. Okay. So we'll write it in that form now. so that the summation is equal to this product. And these are all the generators of those geometric series where the ratio is 1 over some prime number to some exponent. Okay. So just one more thought before we move on. So we always write 1 minus the ratio, right, whenever we're doing this, because that was how we performed the simplification. So I want to show that if you end up with okay, so this is the general form, but if r is less than 0, right, set r was equal to negative t, then your series would become say we start getting these alternating terms. So over here, it simplifies to 1 plus t, and then every other term is negative over here. So it's alternating in sign. So if the ratio is negative, then this, whenever you expand it, it becomes this sum with alternating terms. Okay, so then why would we expect this? For one, why should we expect this function to have any say in what goes on once you move s past the harmonic series point, right? Past the divergence that occurs whenever you reduce this to the harmonic series with s equals 1. So it seems somewhat invalid to really discuss it. And so this is what's known as analytic continuation. So there, in complex analysis, each region of definition, functions tend to be defined as in terms of some region where it converges. So we typically look towards summations like this, and we say that this defines some function, and it's usually so you pick something, right? If this is the complex plane, and these are your input parameters for s, right? Then there's some region where the function is defined. And then we look around that region, usually starting at the border, right? And then you see, like, you just sort of poke it in that direction. And I think it's most common to go either purely in the real axis or purely in the imaginary direction. And you poke it, and you see, well, if I add up all of the numbers with inputs over here, does it still converge? Does it still add up to something finite? Or is it nonsensical? Does it diverge? Or whatever. And so we've already established that this point right here doesn't have a definition. But if you do that prodding, you find that you can extend this function basically around that point. And so if you extend it, then there's a theorem that says, well, then at that point you have some new function, right? Because this was only defined over here, and now this new, more magical function, this new, more magical version of it is defined over this bigger region. What gives, right? Do we have two functions that are overlapping each other? And no, we actually have this guarantee of uniqueness. And so what happens is that this is you can think of it as a simplification of a function which is defined on a much larger region. And whenever the input right here happens to be over here, the function reduces really nicely to something that looks like this. But when we extend it to this region, right, everything except for this point, but adding in this region, right, then we can write the function as related to something called the Dirichlet Eta function. And we'll take a look at that in a second. And so that's how we get our values for this region, right, and how we know that it can be defined in that region. And then, so we extended it there, and then if you investigate the function further, you'll see that there's a functional way to write the equation. So we had this functional representation for the gamma function. Well, we write it in terms of this evaluation of that same function at some other point times a constant. Right? We're able to simplify it and evaluate it somewhere else and then derive the value. And so that's kind of a hallmark of functions which have been continued via analytic continuation. So you have this region where it behaves real nicely, and then you have this other region where you can define values for it, but you're essentially hopping your way to get there. So you have this area that's really nice and friendly, and this other area that you can demonstrate that it holds this result and that it is related to this well-defined region, but you have to sort of jump through some hoops to get there. And it's basically just this continuation, right? So we've extended our function's definition into this strip, and then through another process, we found a way to define it where so this is zeta of s. Both of these are just ways of writing the same function, zeta. Okay. And so the functional equation is something like so it's, if you want to know zeta of s over here, it's something, so right, foo, some placeholder, something, times zeta of 1 minus s. So to know it over here, you do something, right? You multiply it by something which depends on s. And then also by evaluating it over here, and so s flips to negative s, but it's shifted a bit, it becomes 1 minus s. So that we have this well-defined region over here, right? Everything over here is defined by either of these equally well. And then the next step was to define this strip here. We call it the critical strip. And we can get at those values, and they're really not so difficult. We'll program our way to it here in a little bit. And then you also have, then if you want to go even further, then you can use something that looks a little bit like this. It's more complicated, right? But it's something times this reflection of the function that we're looking at. And so in that way we're able to define it everywhere except for right here. And so you can kind of see that, s and 1 minus s, everything kind of pivots around this point of where the real part is 1/2, right? So so from this form, whenever we extend it, we see that if you put in negative even integers, right, so starting with -2, then this function, which is never 0 over here, right, because we're adding up a bunch of positive values essentially at the beginning, but if you go off of the real line, you can start to get some negative summations, right? But it's never 0 anywhere over here, and so when you plug it in and you start reflecting it around, even though it's never 0 over here, part of foo, right, part of this placeholder, is sine of pi times s divided by 2, so that at all of the negative even integers, the function is 0, right? So never 0 over here, 0 infinitely many times in this direction on the real line, right? Whenever s is divisible by -2, okay? And then this region that we don't know a whole lot about. So it was discovered, pretty early on, that there were points in this strip, in this questionable strip, right, between 0 and 1, where the function was 0, but it is remarkably irregular, and it's something that you might expect given something that is an infinite product of every prime. So we might expect it to be a little bit irregular. And in fact, every other time that we've viewed functions as this product, it's been a product, it's been something like a polynomial where we take the roots and then we multiply them together. And here we don't have that. So how is it that we would ever expect it to be 0? And so we'll see that. Well, I mean, let's take a look. Let's break it down, right? Okay, so this is the region that we want to know about. This is a critical strip that has some non-trivial zeros in it, and we'd like to know where we might expect to find them. Okay, so the eta function is this, like it's very similar to this. Okay. But the terms alternate, right? So before we had 1 plus 1/2, now it's 1 minus 1/2. And so minus 1 over 2 to the s, plus 1 over 3 to the s, minus 1 over 4 to the s, and so on and so forth, right? The alternating version of this one. And so okay, so let's do another algebraic trick here. I'll just write out the first few. Okay, so it's this. Zeta is this, right, in the region that we're discussing. Okay, so we're going to multiply by a clever form of 1, right? And it's really only 1 sometimes, right? At the periodic points where this is 2 over 2. So whenever s is equal to 1, that's the case. Whenever s is 0, this is just 2, right? But the reason that we have the s in the denominator is because it makes the denominators compatible. So when we multiply this out, right, like this is 2 over 2 to the s, right? When we multiply it out, so let's see. Then now we have this series that's 2. It's a series of summations of 2 over the even numbers, right? Ways to the s. So 2 over 2 to the s plus 2 over 4 to the s plus 2 over 6 to the s, which you would expect because we multiplied both the numerator and the denominator by 2, or something really similar to that. Okay. So now we want to be able to relate these back to that eta function somehow. And so we're going to do it similar to the way that we identified the geometric series. So we'll rewrite this right here in one line, and then we'll perform the operation. So the even ones. And now we perform the subtraction, the same trick that we did whenever we were working with creating the geometric series in the first place. Okay, so subtracting this from this one, right? So 1 minus, well, there's no corresponding 1 there, right? So 1. And then minus this version, right? So 1 over 2 to the s minus 2 over 2 to the s. Well, that's negative 1 over 2 to the s. There's no corresponding 1 over 3 to the s in this one. So the 1 over 3 to the s goes through unmolested. And then the next one is 1 over 4 to the s, right? 1 over 4 to the s minus 2 over 4 to the s. Well, that's just minus 1 over 4 to the s. And so now we have this alternating series, which is exactly the eta function we were talking about, where it alternates terms. And so these two are related just by this simple value. Well, this this is well defined everywhere except for well, it's 0 whenever s is equal to 1, and so it makes sense that we have we've essentially, whenever s is equal to 1, this goes off to infinity and this goes to 0, and so 0 times infinity is typically undefined, but that is kind of the heart of analysis. You take a look at that and you find out, well, if I add infinity to anything finite, it's always going to be infinite. Same thing if I subtract it, we're going to run into the same problem. If I multiply it, well, sometimes when I multiply infinity times 0, I end up with something that resolves to a thing, right? And we've looked at one example of that already. So the limit of sine of x over x as x goes to 0 is 1. So that's 0 divided by 0, or 0 times infinity, either way, and it resolved. Now that's not a rule, right? And we don't know what it resolves to, but it has the potential to resolve to a constant, and that's when we perform analysis, is to find that out. And so now this function eta of s, it actually is defined at 1, the point where s equals 1, where the harmonic series diverged, right? And 0 times infinity sometimes works out that you get something finite. And it turns out that that all the way up until s equals 0, that this new function still continues to converge. Okay, so this converges everywhere that we want it to within the critical strip, and we can compute it. It's not so bad. Again, we will code it out here in a little bit, and so we can actually compute values of zeta of s by computing this sum, right? And then correcting it, right? So okay, so if we just move this factor over to the right-hand side, right, if we divide both sides by 1 minus 2 over 2 to the s, right, then just by this trick of multiplication, we're moving a scalar value, right, because once you pick s, this is just a scalar, right, and it's defined everywhere, right, but now we've reintroduced the singularity, the pole, the infinity, at s equals 1, because remember, this was 0 when s equals 1. So now we're dividing by 0, which makes sense, right? So eta of 1, right, this has some constant value. It has this well-defined value, this convergent value, whenever s equals 1. But we know zeta of s is infinity because of the harmonic series at s equals 1. And so we've kind of reintroduced it there. And so now, in this representation, you can see that this function, it was really this function hiding all along, right? So this was defined really everywhere that we wanted it to be, except for the point s equals 1. And so there's that relationship, and that reduction remains clear everywhere except for in the critical strip, right? Right here on the real line between 0 and 1. But everywhere else it's still really well defined, and it's just a constant. Right? And so, if you remember, if you substitute in from over here, right, then you get this sort of seemingly vacuous statement. So just substituting, right? Over here we had eta of s was equal to zeta of s times 1 minus 2 over 2 to the s. And then we got this form from it. And then over here we can see that we're really just using associativity, right, to show that that it's related to the zeta function. That when this can be removed, then it's really that simple. But there are these points where zeta of s is essentially blind to what it really is, right? When we define it in these terms, right, and that would be within the critical strip, and that's whenever you have to use its slightly truer representation, which is that eta form. But again, we can see it's just associativity. If we group the parentheses around these two, then it reduces back to that simple zeta function. But again, like you have to use this version to extend it into that region, and so it's a little confusing going from this simplified version and then creating these more and more complicated versions that are continued to these larger domains. But it's a little bit easier in the other direction, where if you surmise that there is one distinct function that performs the mapping operations from domain to range, right, and for those complex functions, and then there are just regions where it simplifies into something really nice, right? So we have this super complicated function, which I will probably write out. Oh, I guess I could write it out for you now. Okay. Right, so this is to extend it to here, but if we want to extend it for the whole plane, right, then we would rewrite it. Can you see that? Yeah, a little bit of glare, but we'll have to deal with it. Okay. So this is that reflected term that I was talking about earlier. And then this is all of everything else that was foo before, right? So the constant 2 raised to the power s times the constant pi raised to the power s minus 1 times sine of pi of s over 2, or times sine of pi times s over 2 times gamma of 1 minus s times zeta of 1 minus s. So it just keeps going, right? But this, it simplifies really nicely when you reduce it down to just the right half plane, which simplifies even further when you reduce it to just the values to the right of s equals 1. Okay, so we know that there is some truer version of it. We just multiply by this constant, right? So so that still holds, and so you can get to that region still using this, right? Like, but if you substitute this into zeta of s, okay, so we're not going to do anything with this probably today. If we do take a look at this, then it'll probably have to happen on Thursday. We might get started on it, but so we put it back in this form, right, where we've just made this substitution. Right? You can see that if we associated them differently, these two would cancel out. Right? And so now we're going to substitute zeta of s for this product definition, right? And so we said that it's not properly defined in that region, but you know we are exploring it. This is analysis, and so we're going to move it from not defined to not defined. Let's take a look, right? So okay, so now we have it in terms of the Euler product, and again we can see that these really aren't doing anything. Like, we're multiplying by it to extend the definition, but they want to vanish anywhere that this converges, right? So it's here kind of as this notational trick to keep the sum from diverging, but but it wants to vanish. It wants to cancel out with this leading term. And even in this region, after we've extended it, this product is still, it still wants to be this valid definition for it. And I will argue that the same is true of this sum, right? Like these want to vanish. We could just as easily have substituted this sum in here, and it wants to go away. But it's that that mapping back to those geometric series, or the product of these geometric series, that that sort of makes sure that we have to keep it in parentheses. We have to make sure that this converges before we undo the work of this, right? And so it's a little like conjugating it into something that converges, right? But okay, so now we've seen it, we've played around with it enough. We're at least halfway into class. So let's jump in and see what we can program in terms of us exploring this. Okay, so we kind of started this last time. We have the summation, and now we have the product as well. So zeta of s is equal to the product over all of the primes of 1 divided by 1 minus 1 divided by p to the s. Okay, and again, these are the generators of those geometric series, right, using all of the prime numbers. So in order to do this, we need to maintain a list of primes. So there's a few ways to get them, but the easiest way is to have a list ready-made, and then to use that. So we're going to use all of the prime numbers from less than 1,000. Okay. So now let's define zeta prod and so it's going to take an input value, but then it's also going to take a collection of prime numbers, and since we're going to use this whenever we invoke it, we'll move it down here so we don't have any confusion regarding scope. So that when we reference primes, we're definitely referencing it within this function. Okay, so just like this, right? We don't need number of samples because we're not generating the terms here. We're generating them from a finitely collected assortment of primes. Right? So then the product, right, prod, begins with the multiplicative identity, and then we're going to loop for p in primes, and then we're going to multiply the terms, right? And then 1 divided by 1 minus 1 divided by p to the s, right? Okay. So now, let me just invoke it. So we expected something close to whatever the sum is for this. So we'll start with the sum for n equals 2, or s equals 2, because we kind of already have that. So then we expected this, and we got this. And then we just print it out. Okay, so let's see how that goes. And you can see it actually worked pretty well. So the sum, let's prefix this. So you can see the sum got one significant digit further than the product. But we could get further by using additional factors, additional prime numbers. So you just include additional terms, and just like with the sum, the error tends to 0 as the number of terms included goes to infinity. Okay. So then we know that there are those non-trivial zeros. So let's take a look at those. Let's take a look at, we'll look at the first two, I guess. Alright, so there's a list of them here. One of them occurs when s is equal, or sorry, whenever t is equal to this. So let's copy that one. Okay, so the real part is always a half, and then this is going to be the complex part, and we mark it with a J in Python because everyone uses iterators. So I is very commonly used. J was more readily available, I guess. Okay, so that's the first one. The next one is right here. Okay, so let's play around with the values in between there. So again, we have two forms. So let's use each. So for this one, we'll do 10. So then we'll call it result sum, and it's going to equal zeta sum for s, and then result pron, that's going to equal zeta pron for s. And then really, if we're going to do this right, we need a control value. So we know that it's properly defined in terms of the eta function. So so let's do it from zeta, or from eta as well. So eta is remarkably similar to zeta. So it's the same one, but then we have that alternating sign. -1 to n plus 1. Eta is a sum. We'll do, sure, 100,000 samples. Doesn't cost us much. Sum, still a sum. And so now we just have this additional sign that we have to solve. And so this is going to be equal to, well, we don't want to have to multiply -1 over and over and over again. So really, we just want to know if in, we'll move this outside. So it'll be 1 by default. And so if in mod 2 is equal to 0, then it's even, and sine is even. Otherwise, it's odd. Let's see, when n equals 1, when n equals 1, it's supposed to be even. Right? So this is the case whenever the sign is +1 whenever n is odd, and it's -1 whenever it's even. Okay, so then now, instead of this, it's sine, right? So either 1 or -1 divided by this. Okay, so that one wasn't so bad to adapt. Okay, so now as we go through and we look at our non-trivial zeros, so this is the eta sum. Okay, so we need one more level of indirection. Right? So now we need zeta from eta. Right? So we remember the relationship, right? So zeta was equal to 1 divided by 1 minus 2 over 2 to the s times eta of s. Okay, so now we have eta over here. It's a reasonably good approximation, so we'll use that for eta. But now we need zeta derived from that, and that'll give us our continued version, the one that's defined in the critical strip. Okay, so this is pretty straightforward. We're just doing this. So we have that eta sum, and then this over here. Okay. So again, you see it's pretty straightforward once you get moving on it. Positive primes. Okay. So now we're going to test it out here, and so we can say that we have an actual result, right? And it's going to be whatever eta tells us it was. So zeta from eta is going to be whatever s is, and then we have the sum if we ignored the suggestion and we just used the sum that we claimed is undefined, and then the product, which again if we ignore the suggestion and then zeta prime set function. Okay, I don't know what it's complaining about, really. Okay, so now we have all of these values. Let's just print them out, and then we'll toy with them. We'll do 1, which is before this, and then we'll do a value pretty close to this, and then we'll do 1 between, and then so forth, and we'll take a look at it. But we'll stay on the critical strip, on the critical line. That is where the real part is 1/2. Because we expect that to be where it's most interesting. Okay, so then if we take from, that's fine. So we have actual sum Okay, let's make sure that runs before we break everything. Okay, so you can see, in this case, the sum, you can see why it's believed that the sum diverges, but if we stick to the product, well, this isn't such a bad estimate, right? So the product formula actually proves to be a better indicator of what's going on in that region than the summation does. And we can talk about it, and they still represent the same thing, right? Those terms still represent the same geometric series that makes up this sum. And we can just see that that what looks like this canceling operation, right, when we relate the eta function back to the zeta function, that it may not always be necessary. So this is where analysis comes in. So when is it necessary to actually enforce that we use the eta function, and when can we get away with using the zeta function? And so that's something that I just want y'all to think about. Let's see. Okay, so we'll pick another value. Right? We'll do the same thing over again. So now we know that the first zero is at this, right? So let's do something really close to that. Now we run it again. Okay, and you can see that it vanished with the eta function, and it vanished over here. And then we got something that appears to be very different. So what's going on with that sum? And essentially, it's just terrible convergence. So what I propose to you is that this sum and this product are actually valid everywhere in that critical strip, except for on the real on the real line themselves. And that's the one time that that the eta function can't collapse down to the zeta function. You can't undo that conjugation. It's essentially blind to the zeta function in that region, right on the real line between 0 and 1. But everywhere else, it looks like it's still doing the same thing. Right? Okay, so let's pick a value in between. Right? We said we'd pick something between 14 and 21 and see. So we did 18 again. It's you can see there's a little bit of error, but it's pretty close. It's close enough to think that that it's ridiculous to say that it's undefined in that region. And then for sake of completion, let's do it with the second zero's value. Okay, and so for that last one, again, it gets really close to 0. So it looks like it actually is defined there, but because it was originally explored along the real line, it was just believed that you couldn't recover this region. And so I would argue that even the sum, which is a terrible estimate, you can look up and down, it's nowhere near where it needs to be, but it's just extremely slowly converging. I don't mean slow like 1 over n to the 1.5 or something like that, right? Or 1 over n to the log n or something like that. I mean like just absurdly slow. I don't know anything to relate it to. but it's essentially waiting for really large stretches of terms in order to cancel out some of the early error that occurs as a result. But that doesn't mean that it doesn't converge and goes to infinity, or as the number of terms goes to infinity. It's just a really bad estimate early on. And by early on, I mean using computable ranges, things that you would pass into a computer. Okay, so that's kind of cool. When we look at it that way, then it looks like the product form is actually beneficial whenever considering this region. It's a little more, it's a little easier to wield. So then, what can we do to gain insights about whenever this function is zero in a non-trivial way? Okay. So let's take a look at that. Over here, okay, so just a review, right? Okay, so we can go in either direction here. So if we have this, then then x squared minus y squared is equal to x plus y times x minus y, and x squared plus y squared is equal to x plus iy times x minus iy, and vice versa, right? X plus iy times x minus iy is equal to x squared plus y squared. X plus y times x minus y is equal to x squared minus y squared. Okay, so okay, so if we apply that to the denominator, then the rule still holds even if it's in the denominator. And so we're going to take advantage of that over here. Okay. So it works out that the exponent is half of the value over here, right? So that, well, 1 over p to the s is the square of 1 over p to the s over 2, right? Like if you square this, you get this. So this is really hiding something of this form, right? And we can factor this all over the place. So that if we're only considering these values, right, just the product form, then we can break it into a product of half these values. so that this so we've reduced it into a product of two terms. This one, right, which still has the 1 minus r form in the denominator, and this one, which still has 1 minus r, but r is a negative value, right? So it's a negative ratio, and whenever you expand this out, you get the alternating signs. So we have the ones that are monotonic signs, and then the ones that are alternating signs, right? So the product of those two series, of this variety, is something that we can compute. Well, we know the value of zeta of 2n, right? Whenever n is 1, right? So whenever it's just zeta of 2, then the result is pi squared over 6. Whenever it's 4, it's something like pi to the 4 over something. Whenever it's 6, it's pi to the 6th over something. But in particular, if we go big enough, right? So if we start with s equals 4, well then this is 4 over 2 is 2, right? So because this is known, right? This is pi to the 4. I want to say over 15, maybe, maybe over 90. I can't remember. Hold on. Got it somewhere. Those known values. Pi to the 4 over 90, yeah. So then this, the one with the alternating ratio, or the one with the negative ratio, we can compute its value by deriving it from these known values of zeta. And so this would reduce to pi squared over over 15. So we can compute its value whenever s divided by 2, whenever s is 4, s divided by 2 is 2. And so we know that value exactly. It's pi squared over 15. And so we can compute these other values from the known zero free regions of zeta. And so this trick of reducing the product into another value of zeta, right? So this holds everywhere that s over 2 is well defined, right? Because the first time that it becomes undefined, is whenever the input function is 2, right, then s over 2 becomes 1. Well, zeta of 1 is the harmonic series, and that diverges, right? So we can't use that one. But everywhere else, we have these computable values for zeta of s. So there's a hole for this trick whenever s equals 2, but then the next hole doesn't occur until s equals 1, right? So that s over 2 is well defined for this entire region between s equals 1 and s equals 2. And so you can continue to creep closer. You see that this continues to be properly defined. But in particular, zeta of s equals 2 is well defined. We know what that is, right? So we have let's see. So we have the representation here or here, or whatever you want to say, right? So whenever s equals 2, it's equal to pi squared over 6. And then still by this trick, right, by this factoring of the Euler product, it's zeta of 1, right, zeta of s over 2, right, which in this case is zeta of 1, times something, right? We don't really know what the value of the other thing is. But again, we've already talked about it. This is where analysis comes in. So if it's anything other than 0, well, this diverges to infinity. So if it's anything other than 0, then zeta of 2 would not be defined. So we know that this product, the one with the alternating sums, has a 0 at s equals 1. Right? And we can check that numerically. We can compute those values and verify that. And so their product, again, infinity times 0, happens to resolve to a constant. But this time it's not 1. This time it's pi squared over 6. But now we know that this form, whenever it's 1 over 1 plus 1 over p to the 1, or just 1 over p, that form, that product, has a 0 at s equals 1. Okay? So now we know that this term goes to infinity whenever its parameter is 1. This one goes to 0 whenever its parameter is 1. But their products continue to be, well defined in that region in between 1 and 2. Right. So now, so the reason that we would expect the first zeros to occur on the critical line, right, whenever s equals 2, is because the first time that we get a 0 from this is whenever s equals 1, right? It's non-zero for all values of s larger than that. Okay, so now this, breaking this down, this would break up into complex conjugate pairs. Right. And again, each one of these we would expect to be zero free up until s got to the point where the real part was equal to 1/2. And then we can relate this form, right? And their magnitude has to be equal because that's the way conjugate pairs work, right? So they're equal in magnitude and they're complementary in argument, so that their sum adds up to 0 or some multiple of 2 pi or whatever, right? They're a reflection of each other about the real axis. But their magnitude is the same, so that each of these would have the same value, essentially the same absolute value. And so it's possible to absorb the I into the exponent here, right? Like, because you're just manipulating argument, and so that these would end up being a shuffling, a permutation, essentially, of the values that you would get on the real line, or even within the critical strip of the eta function, the zeta function as it's defined in the critical strip. And these are non-zero, right? These values, which are equivalent to the permutation, these are non-zero everywhere for the real part of S greater than 1/2. So the Euler product, if we allow it to extend into the critical region, and there's very little reason not to do so, then we get, through a series of manipulations, we get an argument that expresses that it's really impossible for these values, right? I'm sorry, this should be S over 4. Right? For these values to be 0 before you get to the critical line, real part of S equals 1/2. Again, these are permutations of the values that you would get in the critical strip. So that is an argument. This is the first argument that we'll make, that it's not possible to have a 0 in the critical strip to the right of real part of S equals 1/2. Right? Okay, so that's all the time we have now. We'll discuss this more again on Thursday. Have a good day.